the objective. One of the thing is that, as we saw from our last session, is to kind of be clear with the types of data that you would see in your research. So in that aspect, we would go through, you know, we would go through, you know, what the analysis plan is, a brief description of what analysis plan is about. Yesterday we saw from a raw data set to a clean data set. Today it's mostly about, given that you have a clean data set, how do we move to a results, right? So what's the process that is involved from a clean data set to a report on results? Some of the concepts that you should know when you're talking about data analysis is, which we already discussed briefly yesterday, on variables and on how we classify different sets of variables, right? That's the prerequisite, very fundamental in terms of understanding data analysis and prepping for data analysis. And then once you kind of be familiar, we'll discuss about briefly on different statistical methods, mostly on two parts. One is on how you can summarize data. What are the different methods that are available for summarizing a given data set? And then about inferential part, like what are the statistical tests that you would use on a given research study. And then we'll try to finish up with an example of how you can draft an statistical analysis or a data analysis plan for a research study. Right, so that's a broad outline for today's session. So as I said, so what we mean by a data analysis plan is a document which we develop to guide, which will act as a kind of a pointer for data analysis. So it kind of it's not very detailed, but it gives you a step-by-step plan of how you would approach the analysis of your data. So what it does is it gives you an assurance and also a path of how the objectives of the research study can be achieved, right? So that's the main aspect of having a data analysis plan. So the plan is actually the plan is actually done prior to the actual analysis. So this is not something that you do while you're doing analysis or after you complete the analysis. This is done right before the actual performance of the analysis. So one of the goals of having this plan is to promote targeted analysis. What I mean by that is, generally, if you don't have a plan, you would get into the analysis and then you would be testing multiple aspects in a given data, right? So you would run so many different statistical tests which may not have a proper alignment. So having a plan gives you which variables to be targeted at the first run, and that makes it more feasible and also very specific in terms of your statistical analysis. One of the problems that it avoids is called as data dredging, which is quite a common problem in doing analysis. What meant by that is, you run so many statistical analysis, you actually risk the chance of finding a false positive result. Because you run so many statistical tests, there could be a positive result just by the chance itself. Like, there may not be any true association or a true difference, but because you kind of run so many, you kind of dredge the data, you kind of exploit the data in such a way that you would find one or two values that are statistically significant, but in truth it may not be actually a true difference. So having a pre-specified plan kind of helps to reduce that chance of finding a false positive result. Then another additional goal of having a data analysis plan is that it gives you a structure. Because you kind of pre-specified it, you have a step-by-step a methodology of what you're going to do and for which objective. You have that structure for your analysis, and because you have pre-specified it, there is also a transparency. And so what it does is, even if somebody else does the analysis to the same data set, or if some other statistician goes through the analysis, the chance of your findings staying constant are really high. It's not like you found one result, but when somebody else does the analysis or someone else tries up some work on your data, but then couldn't reproduce your own findings, that scenario is very unlikely if you specify the data analysis. That is an important part, because many of findings are very hard to reproduce at present, because there's a lot of data dredging that happens while doing analysis. So that's the overall aim of having a plan pre-specified before you actually go ahead with the actual data analysis. So the elements of what goes into a data analysis plan, the first and most important part are the research questions and the hypothesis. If you have any specific hypothesis, then that's the first part of it. And as you most of you know, the research questions and hypotheses have to be as clear and specific as possible, because those are the ones which would guide all the rest of the points which are put down below. The next point is about the criteria for inclusion in the analysis. So in your protocol, you might have very specific criteria for inclusion and exclusion. That is for in your research study. Likewise, if you have any specific criteria for inclusion in the analysis, then that gets listed as a second element. The third part is the data set. As we discussed yesterday, we talked about some of the principles or practices that are related with having a structured database. And the data set would have variables, and a subset or majority of the variables in the data set will be used in the analysis. Then comes the main aspect of the data analysis plan, where you specify what methods would you use to screen and summarize variables, and what are the specific methods that you use to answer your primary research questions, and then if you have any secondary research questions, what statistical methods that you would use to answer those questions, and if you have any subgroups to be examined, then you put down those subgroups in the plan itself. Right, so because you specify all these things, that you would be interested in, say, 3 primary research questions, and then you'll be interested in a couple of other secondary questions, and then you wanted to look at subgroups as further stratifications in A, B, 3 populations. All that is being pre-specified, so the chance of you doing, as I said in the previous slide about a fishing expedition, is quite less, right? And once you have this kind of a setup, then it leads to a generation of what we call it as table shells. Like, you may not have filled in tables, but tables with skeletons, so that can be used in your research, in your results. So just going back on certain terms commonly used, one, as we discussed yesterday, a variable is a very key term. So everybody needs to understand that very clearly, what we mean by a variable and what are the different types of variables that are involved in. So as we saw yesterday, like if you have a case report form and we collect information on a range of items, then each of those items is considered as a variable, right? Because that varies from one person to other, or one patient to another. So things like age, sex, and religion, and weight, height, and all of them are considered as variables. The important part is that variable is classified based on the type of values that it takes, right? So you look at what kind of values a particular variable takes on, and depending on the type of value that it takes, we kind of classify those variables, right? So that's the first system of classification that one has to understand to put in a data analysis plan. So most of you would be familiar with it. Maybe you have heard it through your E1 or E2, but just kind of reviewing it, and these basic classification systems. The first one is called as nominal variables. Here the values are just names; they're just labels. For example, if you are collecting data on residents, The value of that variable could be urban or rural. As you see, they are just labels, and those labels are classified as nominal variables. Likewise, gender, you have two categories, male and female. uh, and then likewise for religion, you have three categories as measured ones, like Hindus, Muslims, and Christians. So those are called as nominal variables, where the values are just names and act as labels. They do not have any inherent meaning in themselves. So if you have only two categories or two broad uh, values, then those are called as dichotomous or binary variables. For example, you can have a study sample which could be broadly categorized into a treatment or an intervention arm and then a control arm, and that variable is considered as a dichotomous or a binary variable. The second type of variable is called as ordinal variable, where the values can be ordered. Right. So in the previous nominal variable, there is no inherent order in the kind of values that the variable takes. So if you say male or female, you will not be able to arrange those values in any specific order. But if you look at an ordinal variable, and if you see the values that it takes, like low or middle or high, and you see that there is a very specific order in which you can arrange them, where the low comes first, people in the low socioeconomic status, and then the middle comes this the second layer, and then the high is the third layer, right? So there is an inherent order that is present among the values of an ordinal variable. Another example could be like a Likert scale, where you have never, sometimes, often, and always. Again, you see that there is an order which is present in the values of an ordinal variable. Likewise, pain scores. So you have no pain at the bottom, and then the mild, then comes the moderate, and then the severe, right? So there is this the order that is present in those ordinal variables. And if you notice, both the nominal and ordinal variables are also called as categorical or non-numerical variables. So that's the first classification of a part of classification of variables, which are called as categorical variables. And within categorical variables, if the categories do not have any order, we call them as nominal. If the categories have a specific inherent order, then we call them as ordinal variables. So the third type of variable is called as discrete. Here, if you notice, the values are actually whole numbers, right? They are not categories, or they are not names or labels. These variables take whole numbers as their values. And most of the time, these numbers result from a counting process, right? So what do I mean by counting process is, if you have a measurement which results from a counting, like if you're looking at number of children in a household, a number of previous illness episodes, then all of them involve uh, counting, right? So the values that result from such a counting process are all whole numbers, and those whole numbers are considered as discrete variables. So when I say whole numbers, what it means is you have clear boundaries between values. So if you have three, this discrete variable can take a value like 2, or it can take a value like 3, but there is absolutely nothing between 2 and 3. So there is no scope for any of decimals that can go between 2 and 3. So that's why we call them as whole numbers, and they are classified as discrete variables. The last type of variable is called as continuous, where the values are actual numbers, right? So they're called rational numbers, uh, which you might remember from your high school math, where it can take any value in the number line. So if you have a number line which ranges from minus infinity to plus infinity, a continuous variable can take any value within that range. So most often these continuous variable results from an actual measurement process. Like if you have an instrument or a scale that you use to measure a particular variable, then the value that it results from that measurement is called as a continuous variable. So things like height, weight, and if you have laboratory measurements like blood glucose, or if you're measuring any particular antibody levels and all that is considered as continuous variables, because the values that it takes can range from it can take any value within its range. So both these numbers, both the discrete variable and a continuous variables, are called as numerical variables. So we saw a couple of slides before, you have categorical variables, which you can either classify as nominal or ordinal. And then you have numerical variables, which you can classify them as discrete and continuous, right? So the classification in a categorical variable is based on whether the values can be arranged or not. If you can arrange them, you would call them as ordinal. If there is no inherent order, then you'd call them as nominal. In numerical variables, you look at the type of numbers that the variable can take. If it can take only whole numbers, you call them as discrete variable. On the other hand, if it can take any value within its range, then you would call that as continuous variable. Okay, right. So that's about the way in which we classify variables in a statistical framework. But we can also, it's also important to understand how variables are classified based on the roles in the research study. The first way in which we can classify is by looking at which variable can be considered as a dependent variable, right? So when I say dependent variable, what it means is a variable which is of primary interest, right? Usually it's one single variable, and what we mean by dependent variable is that whatever value it takes, it depends on other values, right? So it's also called as an outcome or a response variable, because it generally arises as a response depending on how other variables are arranged, right? So one example, let's say if you're looking at influence of a diet program, a pregnancy diet program on maternal weight gain, we consider the maternal weight gain as dependent variable. The reason why we consider maternal weight gain as dependent variable is because we kind of assume, or we hypothesize, the weight gain will depend on the pregnancy diet program, right? So the response on maternal weight gain is based on which diet program women is on, right? So if there will be a high or low in the maternal weight gain will be decided by the type of diet program the pregnant woman is on. So that variable is called as the dependent variable, right? So that's the first thing. So we must be able to classify a given variable as whether it is a dependent or an outcome or a response variable. So you can also look at the equation here. So generally we consider this y as a dependent variable because the value of this y depends on whatever the value of this x is, right? So if you know the value of x, you'll be able to predict what the value of y would be. So the value of y is called as the dependent variable, and this x is considered as the independent variable, right? So most of the time what we are interested is in finding out the relationship between this x and y. So if you know this value of x and if you know what this relationship is, then you would like to kind of predict or come up with this value of y, right? That's a large part of what we do in data analysis. So as I said, so you also have an independent variable. So that is the variable that influence or have an effect on the dependent variable. So if you have an independent variable, the example that we discussed, the diet program we assume or hypothesize would somehow make a change or affect a change in the dependent variable that you've chosen. In this case, it's the maternal weight gain. So we expect there will be a mechanism through which the diet program would kind of influence the weight gain, right? So that variable is called as the independent variable, which is expected to have an influence on the dependent variable. It need not be one single variable. There could be multiple independent variables. Those multiple independent variables are otherwise also called as exposures if it's an observational study, or they're also called as predictors or explanatory variables, right? So we have two sets. One is called as independent variable, Usually it is one single variable. We also have independent variables that are known to influence the dependent variable. It may be more than one independent variable. The third set of variables are called as confounders. Uh, these are variables that are known to affect the relationship between the dependent and the independent variable. Right? Suppose if you're interested in the relationship between the exposure variable and the outcome, you might have a third variable which could actually confound this relationship between exposure and outcome. So those variables are called as confounders. So you might ask me how we would know about these confounders. That's little that requires either prior knowledge, or you need to have prior experience and expertise, or then you have to look at previous studies that might throw some light on from the review of literature on are there any confounding variables, and if there are, then are they being included in your study? Right. So in this case, for example, like if you're trying to look at the influence of diet program on maternal weight gain, uh, socioeconomic status could be a confounder variable, right? So for example, if you consider socioeconomic status as confounder and diet is the exposure, and then you see what is the effect of diet on maternal weight gain. So there could be a chance that people in the high socioeconomic status could have a different diet, a better diet, and likewise people in the high socioeconomic status could also have a better maternal weight gain, right? So whatever relationship that you might have seen between diet and maternal weight gain could probably be explained by the socioeconomic status, right? So in this case, socioeconomic status is a variable that could possibly confound the relationship between exposure and outcome. So those are the three sets of variables that you are mostly interested in classifying a variable in terms of the roles they play in the research study. You have outcome variable, which is the main primary variable of interest. Then you're looking at exposure variable that would influence the outcome. And most of the research study is about unpacking the relationship between exposure and the outcome. Then you also have a third set of variables that could confound, that could distort the relationship between exposure and the outcome. Right? So let's say going on with this example on maternal diet on weight gain, these are the list of variables, let's say you're decided to collect data on few demographic information, and then you have, let's say this is an interventional study or this is an observational study looking at diet group, and you have two diet group, one gets an interventional diet group and then the other one is the current standard, whatever the current standard is, and your variable of interest is weight gain. So if you employ the first set of classifications, that classification will depend on the type of value this variable takes, right? So you look at what values that age can take, and then based on the values that this variable age can take, you classify them as either numeric or non-numerical or discrete or continuous or whatever it is. Then you have a second type of classification which is based on the role that they play in the research, right? So if you look at age, then you kind of step backward and then see what is the expected role of age in this study that aims to look at the relationship between maternal effect of maternal diet on the weight gain, right? So this is how it would probably go. Like you take age, as I said, you look at what values it can take, because it can take any value. Let's say for in this study, this hypothetical study, it's been set in such a way that anybody between the age group of 20 and 40 can be enrolled. So because it can take any value between its range, you consider as a numerical variable and further classified as a continuous variable, right? And then you look at religion. The values it could take are probably three different categories of religion, and those categories do not have any inherent order. So you call them as categorical variable and further classified as a nominal variable. Then you have measured socioeconomic status as three levels: low, middle, and high. These are categories, so you call them as categorical. But you also see that there is this order that is present among those categories. Low comes first, and then comes middle, and then comes the high socioeconomic status. So you further classify them as ordinal variables. Then, let's say you also measured years of education. You recorded them in completed years of education. So they all are whole numbers, which can range from 0, meaning illiteracy, to all the ways of 20 years of education. So because they are numbers, you classify them as numerical. And then because they also are whole numbers, you classify them as discrete variables. Then, let's say you have two groups. One, the group one gets a new intervention in terms of diet, and then group two are the controls who get the standard of whatever is the current standard of care, right? Because these are two different groups, categorical, and you also see there's no particular order, so you call them as nominal variable. The final variable is the weight gain, so which you measure. So as you know, it could be in positive, like if the weight has improved, but there is no guarantee that it would actually improve, it could deteriorate as well. So the range could be anywhere in minus and also in plus. So it's considered as a numerical variable, and because it can take any value in this range, you consider it as a continuous variable, right? So that's the first part of the classification. Then you look at each of these variables, and then you see what role does it play in this particular research study. So we start with weight gain because that's our main variable of interest. We call them as a dependent variable or outcome variable. Then you're looking at how this diet program can influence the weight gain. So the diet program is the exposure or the independent variable. Then you also have few other variables that you measure, which you probably considered as a covariate, which could also have an influence in the on the outcome. So you measure those variables as like baseline variables in your study. Then you might also consider, for example, you might from the previous studies, you might think age could also be a confounder. You might consider socioeconomic status as a confounder. So this is decided based on the review of previous studies and your prior experience on that particular field, deciding what role these variables actually play in analysis, right? So then you can take that table that I showed you, you can even have it as a graph, where mainly your interest is on the weight gain, and you're trying to see how this diet program can influence the weight gain. That's the main objective or the primary question. But you also notice that few other variables could affect the weight gain, like maternal age could affect the weight gain. There's a possibility that religion could also affect the weight gain, education, and also socioeconomic status. Right? So the arrows all point to a variable which we consider as the dependent or the outcome variable. But there could also be associations between these variables. Right? The diet could be, as I said, diet could have an influence with socioeconomic status. Maternal age, there could be a relationship between maternal age and diet. There could be a relationship between religion and maternal diet, right? So those, when you lay it out in a graphical format, it helps you to see how variables are related with each other. And you would be able to see which are the variables that you are interested in, and the relationship between them that are of primary interest, and then the relationship that are of secondary interest, which would further help you to kind of decide on the analysis methods. So that's the first part. The second part is to look at what goes into the data analysis plan. So I briefly said about the study questions and the objectives. The need to have very clear study questions and very clearly specified objectives. So then you look at the objectives, and then you look at what are the objectives that could be considered as primary objectives or primary aims of the study, and the other aims are the secondary aims of the study. And for each one of those aims, you will be able to list out, okay, what methods do we use as descriptive statistics, what methods do we use as inferential statistical methods, and then what kind of table shells or skeletons that we need to have for the results, right? So those are the main components of a data analysis plan. So when we talk about descriptive statistics, I'm sure most of you would have heard about many of these methods. It starts with the simple frequencies, right? So sometimes You just need to list out all the variables, get a frequency distribution for the variables, which would say how many are there with a particular value of the variable. So if you're looking at number of children in a household, so you can say how many households have 0 children, how many households have 1 children, how many households have 2 children, likewise. So that's called as a frequency distribution. It will tell you the shape of the distribution of the variable. Then you can calculate two summary statistics. One set of summary statistical methods are called as measures of central tendency. The other set is called as measures of variation, right? So under central tendency, you have mean. The most commonly used is the arithmetic mean, where we take an average, we just sum up the values and divide by the total number. That's the arithmetic mean. We also have median, which stands for the middlemost value in a set of values, and you have mode, right? So the modal value is the one which has the largest frequency. So these are the commonly used measures of central tendency. And then you have measures of variation, which will give you an idea about the spread that is present in the data set. So you have the simplest one is the range, where you take the minimum value and then you take the maximum value. You take a difference between the maximum and the minimum. That will give you a range that is present in the variable. And then you can calculate what's called as a standard deviation, which will also give you an idea about the spread or the variation that is there in the set of values. You can also calculate what's called as an interquartile range, like how we take range as minimum and maximum. Interquartile range is the difference between the 25th and the 75th percentile. So instead of taking just the minimum and the maximum, you calculate the 25th percentile, you calculate the 75th percentile, and then you calculate the difference between the two, and that is called as the interquartile range. So it's a kind of visual summary of the descriptives. So if you kind of plot the data, mean is the value, or the measures of central tendency are the ones around which most of the other values are clustered about. Right? So mean is the value, is the peak, right? So that's called as the mean or the median or the modal value. And then you're also looking at sometimes the distribution may be single, where the peak is just one single peak. Sometimes you could have a bimodal distribution where you have a peak and then a valley and then a peak again. Sometimes you could have multimodal distribution as well, right? So that about the peak of the distribution. Generally, the measures of central tendency would give you an idea about where the peak is, around which most other values kind of cluster about. The second aspect, which I told you in terms of the spread, so that is what is captured by the standard deviation. So it's not just the peak that we are interested in, which is captured by the central tendency measures. We are also interested in how spread is the data. Like, is it all tightly peaked, or is it kind of spread across, kind of plateaued? And that is captured by the standard deviation here, the sigma. So if the distribution is a nice bell-shaped curve, then you would expect about 95% of data to lie between two standard deviations. So if you actually count up all these percentages and you see what's the percentage that lies between +2 standard deviation to -2 standard deviation, then you would see that about 95% of the data lies between these two standard deviations, right? So about 5% of data that lies outside of these two standard deviations. So if you know the peak, and if you also have the idea about the spread of the values, then you would be able to summarize the distribution. Right? So if you know what's the average, and if you know how much is the standard deviation, then you can plot it and see, okay, the average is, let's say the average weight is about 60 kilograms, and then let's say the standard deviation is about 10. So that gives you an idea, saying that, okay, the peak occurs around 60 kilograms, the standard deviation is 10. So you would expect 2 standard deviation down would be 40 kilograms, and then 2 standard deviation above is about 80 kilograms. So that's how you would see the curve, right? So you see the curve, peaking at 60. and 95% of the sample to lie between 40 kilograms to 80 kilograms, right? So with a huge set of sample of values, using mean and standard deviation, we could kind of summarize the entire set of values with just these two measures, the mean and the standard deviation. You could also look at it as a box plot, which is here, where you plot the data and then you see where is the minimum value, then where is the maximum value, and then the median is the one which divides the entire set of data into two equal halves. And then you take the lower half, you divide it into two equal halves, that becomes the 25th percentile. And you take the upper half, and likewise you divide it into two equal halves, that becomes the 75th percentile. So if you have these are called 5 summary measures: minimum, the 25th percentile, below which 25% of values lie. The median is the 50th percentile, below which 50% of value lies. And then you have 75th percentile and the maximum value. These 5 provide a summary measure called as a 5 summary measure for the data set. So that's the first part, where we try to come up with some descriptive statistics that can summarize the variables, right? So that would tell you where the majority of values are clustered around, and that would also tell you about what's the spread or the dispersion in the variable. The next part is on the inferential statistics. What we mean by statistical inference or inferential statistic is that you have a population, but then we mostly don't get to work with the entire population, right? So the population could be it's the population of diabetics, or it's the population of people with a particular condition. So it's really hard to do a study on the entire population. So almost 100% of the time, what we do is we take a sample, right? We calculate a sample size, and then we take a sample, a random sample, and then we work with this random sample. Either it's a randomized control trial, or it's an observational study, or it's a retrospective study, whatever it is, we only get to work with this selected sample, right? And once you have the sample, you collect data, and from the collected data, you would make these you calculate these different summary measures, right? If it's a continuous variable, you would calculate means and standard deviations. If you have groups, then probably you would look at the differences in the means between those groups. If it's just a categorical variable, you would look at percentages. And if you again have different groups, then you see what's the differences in the percentages. So you calculate these different measures, otherwise called a statistic. But then once you've calculated them, your interest is to actually see how does this apply back to the population. Right? It's not just about the sample that you have taken. Well, you have taken the sample, you worked on that sample, collected some data, but then you want to kind of extrapolate the results. This generalization of the results is called as the inference. It's a problem of inference, because you're inferring from a small sample to a large undefined population. Right? So that's called as a methods for inference. So under statistical inference, there are 2 broad ways in which we make inferences. One is called estimation, where we get this point estimate. It could be a mean, and then using different statistical methods, you try to come up with a range, right? Which is what we call it as a confidence interval. So this could be an estimate that we obtain from the sample, right? This could be the average weight gain, and then using the data that we have and with the statistical methods, we try to come up with a range to kind of explain that error that would have crept in by taking a sample. Right? So this might be the weight gain in the sample, but if you have to do it in the population, the weight gain could be as low as what we estimated, and then it could be as high as a particular value, right? So that would give you some amount of uncertainty if you have to extrapolate your results from one single sample to a large population, right? So that's one branch of statistical inference where we try using methods of estimation. So you would have seen these kind of plots where if it's, let's say, if the outcome measure is a measure of let's say relative risk, where one means the risk is equal in both the groups, let's say the treatment and the control. But then if you have this, if you have relative risk on this side, it could mean it favors the control, and if you have on this side, then it could mean it favors the treatment. So you have this point estimate here that could be the result that is obtained from the study, and you also see how the confidence intervals kind of extend on both sides, right? So that's how you capture the error that could have been possibly there because we have just taken one sample from a large population, right? So this is also otherwise called as a margin of error. If you have a very narrow confidence interval, then it's most likely that margin for error is quite smaller. But if you have such a wide confidence interval, then it means that any of these possible values could be the population estimate as well, right? So your estimation is not so precise from that particular study. So that's one branch of statistical inference. The other one is most commonly used is called as the hypothesis testing, where we put up a hypothesis and then we test on the validity of the hypothesis, whether the hypothesis is true or the false. Right? So again, the methods, the specific test that we use depends on whether the variable is continuous. If the outcome variable is continuous, then we summarize it by means, and then we use probably t-test, right? If there is just one single sample, then it's a one sample t-test. If you have two groups and you want to compare the means of those two different groups, then it's a two sample independent t-test. If you have one group, but then you have a paired sample where you measured a particular variable before, and then you measure the same variable on those same samples after intervention, then it's a paired test. Likewise, if the outcome is a binary variable or a categorical variable, then we summarize them using proportions, and then we use what we call it as a z-test or a chi-square test to see if these proportions differ from an hypothesized value in case of a one sample z-test, or if you are comparing two proportions, then it's a you're comparing those two proportions, seeing if those differences are indeed statistically different. Right, so that's called as a two sample z-test or a chi-square test. So generally what comes out of these hypothesis tests, like how we do estimation, we get confidence intervals. When you do hypothesis test, the result is what's called as a p-value. Stands for probability value, which ranges anywhere from 0 to 1. And we generally look at, we have a threshold of 0.05. If the p-value is less than 0.05, we tend to call them statistically significant, and then we also have different intervals of p-values to kind of label them accordingly, right? So the value that or the output or the result that comes from hypothesis testing is that of a p-value, and when you do an estimation, then what we get is a confidence intervals. So p-values are very commonly used as a measure of statistical evidence. The framework in which we work is very important to understand. So this is more like a very simplified version of how the hypothesis is being tested and how you interpret the p-values. So you would have your own research hypothesis, or what we call it as an experimental hypothesis. Right. So in this case, in the example that I've been tracking in terms of diet program and maternal weight gain, the experimental hypothesis would be the maternal weight gain is influenced by the diet program, right? Or the diet program has an effect on maternal weight gain, and then you from there you kind of generate a null hypothesis, which would just be opposite to the experimental hypothesis. It's diametrically opposite to the experimental hypothesis, which would state that there is no effect of the diet program on the maternal weight gain. So those who get diaprogram A would have more or less the same amount of weight gain as compared to those who are in maternal diaprogram B. So there is absolutely no difference between these two groups in terms of maternal weight gain. Right? So that's the null hypothesis or the scientific hypothesis. So you have experimental hypothesis, which is what you want to prove from your research study. And then you have a null hypothesis, which would say the exact opposite of the experimental hypothesis. Then you would go and collect data, like you would, if it's a randomized trial, you conduct the trial, you get the data. And then the most important part of the statistical mechanics is that you try to calculate the probability of getting the data that you got, assuming this hypothesis is true. If this hypothesis were to be true, that is, if there is no difference between the two groups, how likely is this data, right? The one that I've observed. Given the assumption that the null hypothesis is true, what is the probability of obtaining the data that I have obtained in my study? If that probability is less, like we have used an arbitrary threshold of 0.05, if that probability is less, then you say, okay, the probability of obtaining this data under this hypothesis is so less, then this hypothesis is to be unlikely, right? So we reject this hypothesis and then we consider the experimental hypothesis as true, right? So we assume that the experimental hypothesis fits the data better than the null hypothesis. On the other hand, if a p-value is more than 0.05, because the threshold is quite arbitrary, if it's 0.05, then we say that it's still plausible. The data is plausible under the null hypothesis, right? And we don't reject or we keep the null hypothesis as a current framework. Right? It's neither disproven nor proven. And this framework is what being used. It's all one of the ways in which it's also used in judicial system as well. Right? So when a person is tried in the court, the person is always assumed innocent. Right? That's a presumed innocence is what the null hypothesis is. And then the prosecutor will collect the evidence in the court and present the evidence to the jury. And then the jury will examine the evidence and see, assuming the convict as innocent, how likely is the evidence, right? So if the evidence is quite unlikely, given the presumed assumption, then you would you kind of reject the assumption, and then you convict the person, right? So this framework is what being used not just in judiciary and statistical inference, but also in many common inferential problems. And the value that we get is this probability value, which stands for the probability of the data, given that the null hypothesis is true. So that's more like conditioning or assuming that the null hypothesis is true. What is the probability of observing the data that you observe? That is called as the p-value. All right, so now we get to the generic structure of the data analysis plan. So it starts, as I said before, it's a clear and a specific research question. The next part is the criteria. So if you have any specific criteria that involved in the selection of samples, that you mentioned them. Then you make a list of important variables in the study, right? And then you put down 4 columns. One is the objective list. The second, where you say, okay, what are the different objectives that I have in my study? Some of them could be called as just a baseline summary of data. Some of the objectives could be of primary of interest, and then some of the objectives could be of secondary interest. Then for each of these objectives, you mention the variables that are involved. Suppose if you're interested in just a baseline summary, then you say, okay, I'm looking at demographic information. 2 minutes. I'm looking at demographic variables, and you mentioned those baseline variables. Likewise, if it's of primary objectives, then you say what are the variables that are associated with the primary objective, and then you look at the secondary objectives and say what variables are associated with the secondary objectives. This next part is where you classify those variables which we discussed earlier in the beginning slides, where either statistical classification or based on the roles that play in the research. And then when you have this table, then you can actually sit with the statistician and discuss, these are my objectives. For each of these objectives, these are the variables that are involved. And for those variables involved, this is the roles that I expect them to play in the research, right? So then the statistician can actually kind of propose what analysis would be more appropriate given these objectives of your study, right? So I'm going along with the example that I told you about in terms of the diet program and the weight gain. Let's say I have the preliminary things like research question, eligibility, and main variable list filled up. Now I move on to the main part where I list out the objectives, and I say my first objective is to describe baseline variables, and I see these are the variables that I'm interested in, like maternal age, religion, socioeconomic status, and years of education of the baseline variables. I would like to describe those baseline variables. So then I list out, okay, maternal age is a numerical variable. Religion, I have measured it as a categorical one. Socioeconomic status is measured as categorical, and years of education is measured as numerical. Then you also specify, are you interested in making any comparisons, or is it just one single group and you are not looking at any comparisons between the groups? So if you are interested in comparisons, then you specify, you are looking at comparison of these values between diet and controls. So then, you can actually propose, or the statistician can actually propose, in summary statistics could be you're looking at mean standard deviation for maternal age, or if it is numerical variable, it could be mean and standard deviation. If it is categorical variable, you're looking at the frequencies and percentage. In case if the numerical variable is not a bell-shaped curve, then you're looking at median or interquartile range, right? So that's the first objective. Then you go and then see the primary objective is to compare the weight gain between women who are in the diet program and then women who are in the control program. So you say the outcome variable is the weight gain, and we discussed that this weight gain is actually a numerical variable. And then, as I said, you are interested in comparing between those who are in the diet and the control. So what would be the statistical test that can help you and say whether the weight gain is significantly different between diet and control? The statistician probably say, okay, we might have to do an independent t-test because we are interested in comparing means between the two groups if it's normally distributed. If you find out that the weight gain is not normally a bell-shaped curve, then probably would use a man-written t-test. The output could be a p-value, or if you're interested in a 95% confidence interval, it could be a 95% confidence interval. Then likewise, you might have another objective to see what was the role of socioeconomic status in the weight gain, right? So again, here the weight gain is the outcome variable. It's numerical. And then because now the socioeconomic status is a 3-level variable where you have low, middle, and high. And you want to compare the average weight gain between these 3 groups. So you probably use a ANOVA or a Pascal values test, again with a p-value or a 95% confidence interval. So you basically list out different objectives. You see what variables are involved in each of these objectives. You classify those variables both in terms of the statistical values and the role they play in the analysis. And this framework would largely help you in your discussion and coming up with a plan for the analysis. So once you have this plan, then this is the plan that you would stick when you're actually going ahead with your data analysis, right? So you would, each of these objectives and these analysis would give you a table that will go into your results. And when you summarize either tables or figures, then you have your result section of your thesis or the result section of your manuscript. And it's clean because you're not went into data dredging or data snooping. It's all done before looking at the data, so you're not influenced by how the results pan out after you actually do the analysis. So that's all this I have for the talk. So what we said is we want to understand the role of the data analysis plan. It gives you a structure and it helps you to target the variables of interest for the analysis. So to have a data analysis plan, you need to have few things. One, the most important thing is to have a very clear and specific research question and hypothesis if you have any. And then you should be able to classify variables both in terms of the nature of values that it takes. That is the statistical classification we call numerical, non-numerical, nominal, ordinal, and stuff. And then you also should be able to classify them in terms of the role they play in the research. So what's the outcome variable? What is the exposure on the independent variable? And do you see any other confounders or covariates that could influence the relationship? And then the last part is in terms of the objectives, the elements that goes into the data analysis plan. We just discussed that. We said the objectives are the important part. Then you mentioned the outcomes, and then you say if there are any comparisons that are involved. The final part that kind of completes the data analysis plan is where you propose a statistical method for each of these objectives that involve different variables or outcomes. Okay. So I'll stop here. If there are any questions, we'll spend about 5 minutes on any specific questions. Do you have any questions on going about having a data analysis plan? So I'm sure each one of you have your own thesis and your research proposal and protocol, and each one of you have to do your data analysis. So if you have to have your own data analysis plan, would you be able to do that?
Usually for arts. Hello, sir.
Huh?
Sir, good evening, sir.
Good evening. Go ahead.
Sir, usually for RCT, how much time will it take, sir, for data analysis and all this? I mean, how many hours generally?
Yeah, it's a good question. So if you have everything sorted out, if you have very clear questions, and if you know what exactly needs to be analyzed, then it should not take a lot of time. Most of the time, what happens is where you start with something, and then it goes in a very iterative fashion, right? So you do something at the first phase, and then you find out, you're left out a few things. You go for the second round, and then you find out, you left out few other things, and then you go for the third round. And when you're doing the third round, you find out there are few mistakes there. So you go clean up the data, and then you come back again for the fourth phase. So it kind of spans quite a lot, where in fact, if you actually plan it out ahead, you can do it in, say, about a couple of days.
It should not take more than 1 week, sir.
Yeah.
We work out per day some 3 hours or so.
Yeah, should not take a lot of time.
Okay. Okay, sir. Thank you.
There's a question about comparing 3 groups and multivariate analysis. So as I said, so if you are looking at more than 2 groups, depending on what the outcome is, either if it's a mean, then it's analysis of variance. If it is proportions, then it is chi-square test that we use. It always depends on what the outcome variables are. So that's the first thing you should be able to decide. And second thing is about multivariate analysis. So far, whatever I've discussed with you is in terms of where we try to look at the influence of exposure on the outcome. Sometimes you might want to adjust, like the example that I told you, we're looking at the adjustment of only socioeconomic status, right? Suppose if you have to adjust for all the variables, let's say you want to look at, you want to adjust for the effect of age, you want to adjust for the effect of education, you also want to adjust the effect of and height, maternal height, then you would go for a multivariate analysis because you're looking at multiple variables and you want to adjust for those other covariates and then look at the relationship between the exposure and the outcome. Right? So then you would use the multivariable or multivariate analysis. Any other questions? My suggestion to you is, as an exercise, I'm sure all of you have your own projects and your own thesis. Take down your thesis and try and see if you can have a table like the one that I showed you, where you list the objectives, and for each objectives you see what variables are involved, and for the variables that are involved, you classify them statistically, whether it's continuous or a categorical variable. And then you say, do you need comparisons? If the comparisons are there, how many groups does the comparisons have? And then try and see if you can also, describe a statistical method. If you're not able to, then it's fine. But that chart that you prepare would be very useful when you're actually discussing with your statistician. That's one. And also when you're trying to put up your results, it becomes easier because you can easily structure your results based on those things, because the plan is based on the objectives. And if you just follow the plan, you will have a series of tables or graphs that will kind of fulfill each of your objectives, study objectives. All right. Any other questions? If not, thank you.